Okay. Hi. So, like Warren just said, I'm going to talk to you about analysis and detection of malicious OLEs using open source tools. But when I say open source tools, what I actually really mean is that we are going to play with them using Snort, specifically for detection of them. So who am I? I am a threat research engineer for Cisco Talos. I work for the outreach team, which means that I spend my time divided between hunting novel threats, trying to find new and exciting malware that we haven't seen before, and traveling to talk at conferences and also speak to customers. Prior to working for the outreach team, I worked in detection response, which means that I did vulnerability research, malware analysis, things along those lines, with the goal of developing detection for Cisco security products, which is a fancy way of saying that I wrote Snort rules and claim AV signatures for a living, and that is what makes me qualified to talk to you about this today. Prior to working in InfoSec, my academic background is in computational astrophysics, which is why I have this picture of this galaxy here. And if you haven't heard of Cisco Talos, we are the threat intelligence division of Cisco Security. This means we do a huge range of threat research on everything from finding vulnerabilities in third-party software to doing signature development for security products to speaking at conferences like this. To give you a brief outline of my talk, first I'm going to intro you to Snort and to the rule language. We're going to talk a little bit about the differences in writing good rules versus just generally being able to write a Snort rule, because to write a Snort rule is actually very easy. To write a good Snort rule is an entirely different matter, and that's why we employ so many people that do this for a living. We're then going to do a super brief intro to OLEs and to these file formats, and then we're going to use two case studies to talk about the ways that Talos detects these malicious OLEs. These are both O days from the last roughly year or two that are still actively being used today, which is why I've picked them for my case study. So like I said, I'm going to give you a real brief, bare-bones introduction to Snort right now. Snort, if you haven't heard of it, is a network IDS that was first created in 1998 by Marty Roche. Amongst many, many other things, it does real-time packet analysis. It's also free and open source and available online. And the rules format is actually text-based and very easy to learn. So you can probably read a Snort rule straight off, even if you've never seen one before, and I'll show you one in just a second, and you'll see what I'm talking about. But actually being able to write a rule well takes a little bit of practice. Unfortunately, I can't really talk to you about all of the cool things that Snort does because I only have 45 minutes for this talk, and I could probably spend a few days talking to you about Snort. So this is, like I said, a really brief, bare-bones introduction to it. So first I'm going to give you a Snort rule just to look at. This is a little bit of a complicated one just because we have so many rule options here. I'm not actually going to explain what this is detecting because this is just a simple malware rule and we're looking for a number of the parameters that the malware is using in its request. But if you've never seen a Snort rule before, this is what they look like. So like I said, it's a text-based rule format and it's maybe not the simplest thing in this case to read, but it's at least English, which is nice. And now I'm going to get into the Snort rule syntax. So the first line of the Snort rule, in any case, will be our rule header. So we have a couple of different things going on here. Our first word of our header is the rule action. So in this case, it's going to alert. This is what the rule will be doing if we do hit and all of our content matches are within whatever we're inspecting. You may also see this be drop, but in general, this will just be alert. Then we have the rule protocol. In general, probably TCP, maybe UDP. We do have other options as well, but these are the most common ones. Then we have our source and port address. Source address and source port. And in this case, they're any, so we don't particularly care what they are. We then have an arrow that shows us the direction of traffic, and this goes to the destination address and port, which can be a specific value, or any, as we have on the left side of the rule. You can actually make this arrow go in either direction, but you should probably never do that. It's confusing to whoever is reading the rule, and it's also just not really convention. And a cool thing we can do with these header variables is use them to group values. Rather than having to list out a huge number of addresses or ports, we can just put them in a configuration file somewhere, rather than having to change them in every rule. Every time that something on our network changes, we can just use them in a configuration format and specify them in some other file somewhere. One that comes up a lot maybe would be the HTTP servers and HTTP ports. We also commonly see file data ports being used, and something that you will probably see in just about every rule that the Talos rule set contains is home net and external net. So these are what you would expect, IPs that are related to your network and IPs that are not related to your network. Every other thing that I'm going to talk about from now on is called a rule option. So on the left in this case, we have a rule option, which would be the message in this case. On the right, we have our argument, which is literally rule message. And the most important rule option of all of them would be our content match. So static strings are the bread and butter for Snort. In order to have a good Snort rule, to have any Snort rule at all actually, you need to have some kind of static string, even if it's just 1 byte. The longer and more unique the string, the better, obviously, for the case of being able to refine vulnerability traffic versus non-malicious traffic, and also for the sake of rule performance. So in this case, this rule is looking for just a string, A, B, C, D, and you can specify this as the actual string or as hex values. And like I said, this just finds a static pattern in your network data, whatever you're looking at. We can also modify our content match. We can make it case insensitive, which is kind of nice if you don't know the way that it's going to appear in your traffic, or maybe this could be used to evade your rule. By default, our content matches are case sensitive, so it's something to keep in mind. We can also specify where in our packet we want to look. So if we use a content modifier called the offset, we want to specifically skip 2 bytes of our packet before we start to look for our content match, which is ABCD. So you can think of this as the beginning of the window that you're going to be searching for your content match. And this is the absolute position in the file. The corollary to our offset is depth. So depth is kind of the terminator of that window that we're searching within. In this case, we have a depth of 4 for our content match, and we want to find these 4 bytes within the first 4 bytes of our packet. As I said, these rule modifiers, offset and depth, are absolute in the packet. The next two I'm going to talk about are relative to previous content matches. So you can use offset and depth if you only have 1 content match, but in order to use the next 2, you have to have at least 2 because they're relative. So in this rule, the first content match we see is ABC. We skip 1 byte because we're specifying that our distance is 1, and then we look for DEF anywhere else appearing in the packet. Like I said, this is relative, so you have to have at least 2 content matches. And we can also use the within modifier to specify where we should stop looking for our second content match. So in this case, we want to match on ABC before checking the next 10 bytes following ABC for EFG. You can also negate a content match. So in this case, we would want to find ABC in our packet and then check the next 10 bytes following our first match to make sure that EFG does not appear. You cannot have a rule that only contains a negative content match, so if you are trying to check that something is not there, you do have to have something positive in your rule. The next thing I'm going to talk about is a little bit complicated because I don't have a whole lot of time to actually talk to you about the processing work that Snort does when it looks at a packet. So Snort is pretty smart and is able to tell what kind of traffic it's looking at. So in this case, for this specific content match ABC, we only want to check the HTTP URI. And Snort is able to look at a packet and decide what is the URI. And we can check only that window that Snort has identified for this content match, which is nice if you're trying to speed up a rule because you're looking at a large amount of traffic. To give you a better idea of all of the ways you can use this, if you take a look at everything in all of the different colors here, Snort is able to identify our HTTP method. We can look at the URI. We can also check any of the headers. We can check just the value of the cookie. We can also just check the HTTP client body. And this saves you a lot of processing time because you don't necessarily want to check every single thing in every single packet if you only have a simple content match. Something I'd like to point out here that we see a lot when people submit to our community rule set is that you should never, ever, ever match on the HTTP method. That would be, in this case, this post here. And the reason for that is that you're not actually doing anything to help limit inspection. So our goal when we write a Snort rule is to limit the amount of traffic that we're inspecting, because this is computationally intensive and slow. So the more content matches you have, the more time Snort has to spend deciding if something is going to match on your rule. So when you use something like post or get, the HTTP method in your rule, you're really not doing anything for the sake of limiting what we're actually looking at. There are some exceptions to this rule, but it's pretty doubtful that you're actually going to need them. So in general, this is just not something that you should use if you're trying to write your own rules. Another content buffer that's going to come up a lot when we talk about our malicious OLEs is the file data content buffer. So this restricts a content match to just the file data. And whereas we have to repeatedly define for our other content buffers which one we want to look at for each content match, with file data we actually only have to include it once. And that's pretty useful because a lot of times we want to identify a lot of things in our file data buffer, and it just makes it quicker if you're an analyst writing this rule. Excuse me. So in this case, we have 3 content matches, and they're all within the file data buffer. Another thing I'm going to point out that's a bit of a more advanced rule option is our flowbits option. So this allows rules to track states during a session. And this would be used in conjunction with a rule that contains actual detection. So this is kind of a fancy way of saying that we're going to use this to identify file types, and this will make more sense when this comes up later on. And probably the most important thing that I'm going to talk to you about in terms of Snort rules is our fast pattern. So this is our entrance condition. If we match on our fast pattern, we're going to evaluate all of our other rule options until we reach the end of the rule, or we miss on a rule option. So we want to keep as much traffic out of the detection engine as we can, because like I said, it's slow, and the more traffic we have being evaluated by a rule, the slower Snort is going to be. So we want to pick the most unique content match that we can. So here in this rule, we've set ABC as our fast pattern. And you can think of this as the entrance condition. Additionally, we have a fast pattern only option. So in this case, that means that we would evaluate ABC and then we would drop out of the rule because we only have the one content match. When we specify a fast pattern, you evaluate it once in the fast pattern engine, and then you would evaluate a second time as we evaluate the rest of the rule options, which maybe doesn't make sense right now, but will make sense when we have content matches relative to our fast pattern, because we're not able to use any kind of distance modifier if we specify fast pattern only. We're also able to use Perl-compatible regular expressions, which is quite nice if you have something that's maybe more complicated than just a static string. And I pointed this out a few times, but one of the most important things when we write a Snort rule is that we minimize what we're inspecting. So we do this first with the fast pattern. We want our fast pattern to kind of decide for us if we're looking at traffic that might actually be interesting and relevant to our rule. We then have things like content matches, the more general ones that we can use to isolate just the vulnerable application traffic. And then we can use the more complicated or more general content matches after our more unique ones to identify just things relevant to whatever vulnerability condition we're trying to identify. And finally, we would go into computationally intensive things like the PCRE or the byte tests, other things that I haven't mentioned in this talk because they're a bit more complicated and hard to explain when I only have limited time. But the goal of this, again, is to just isolate traffic that is relevant to our vulnerability, whatever we're trying to identify, or if you're just trying to identify malware traffic. So now I'm going to give you a very brief intro to Office file formats. So for the first file type, we have an RTF. We have a file magic consisting of what is in green here. And in an RTF, you'll see a number of control words that are delineated by a backslash. And each of these control words has a different action. For example, the /par would indicate that you're looking at a new paragraph in the file. RTFs are relatively simple, so there's not a whole lot for me to say about this. The more interesting file format are Doc and Docx files, which you see more often. So Doc is the legacy Office file format, whereas Docx is the newer one since 2007. Docx is actually just a zip archive of XML files that has a particular structure. And the one that we really care about in this case is word/document.xml. That's usually where you would see, at least in what I'm going to talk about, something that would be relevant to an exploit. And now I'm going to get to the actually exciting part of this talk, which is the section about malicious OLEs. So for this portion, I'm going to talk about two specific O-days that we see relatively often, the strategies that we use at Talos to actually detect these files. The first one I'm going to talk about is CVE-2017-0199. You may have heard about this because it's so commonly used as a dropper. Even today, we still see this being used quite actively, and generally this would be used to go out and grab other malware that would then infect your system. So you would see something exploiting this CVE, maybe being used in like a phishing campaign, and then someone would have to download it and open it. And unfortunately, that happens quite often. So this is successfully used quite a bit. And again, like I said, these are malicious RTF documents, and they contain an embedded OLE, which is kind of unique that you would see that embedded in an RTF. And these OLEs are abusing the URL moniker in order to make outbound HTTP requests, which are then used to grab and drop other malware onto your victim machine. If you've never heard of an OLE moniker, according to Microsoft, they're used to identify, connect to, and run OLE compound document link objects, which is a complicated way to say that it's used to make that HTTP request to the attacker-controlled domain. So the important part that actually matters for us is this value right here in green. And I've thrown that up there just so in the next slide you can kind of look for what I'm talking about. The way that I've set up these slides is to kind of, one, explain the mechanics of what is going on, and then to give you guys an example of the way this actually looks when you're hunting through things as an analyst. I've put in PCAPs of the malicious files as well as chunks of the files themselves that are relevant to these exploits. So what makes this malicious? If you have a sample and you are working in something like detection response, you may get something and you have no idea if it's good or bad or what it's doing. Maybe a customer has just said that, oh, this is bad, we think it's doing something, or maybe you have no idea at all. And so maybe in order to get an idea of what you're seeing, you'd pop it into a sandbox or open it on an isolated system and see if you can get any network traffic. If it's malware, it probably has some kind of network functionality, at least for the type that I'm concerned with, which is maldocs. And so in this case, I threw this sample in a sandbox and it made an outbound HTTP request, in this case for something called template.doc. And if you further inspect this request, it maybe looks a bit normal. Template.doc isn't like particularly alarming necessarily. The headers seem normal, but if you take a look at this host, we have this long randomized host name, and that's probably not anything normal. Normal people don't really go out and register domains that look like this. So that's kind of sketchy and indicates to me that, yeah, this is probably bad traffic, even though we got a 403 and I don't actually have the file that this is requesting. There were, of course, other files that did grab actual malware, so that's also a pretty good indication that this is bad, but 403 with a sketchy domain is also a pretty good sign. So now I know that this file is malicious, and I am going to go ahead and start hunting through this because I'm an analyst and it's my job to try and write a rule to detect this. So I go through this RTF, and this is a very small chunk. At some point there is an embedded OLE, like I mentioned before. And then if we look at the contents of this OLE, it's kind of a bit boring to look at, but like I mentioned previously, we end up seeing, and it's highlighted here on the slide, I don't know if I have a laser here, maybe, right here. That string that I threw up earlier is now in the file. So there you go, that seems kind of unusual. And if you take a look just after, we see some bytes, and then we see another set of bytes, and because I look at this all the time, I see some ASCII readable characters in here. Not that I have the hex table memorized off the top of my head, but in that case, I know those bytes. And they're followed by nulls, which makes me think that this is a Unicode string. And if you translate this to actual readable bytes, we see this request URL, which is what we saw in our PCAP earlier. So now we saw the request for template.doc and the PCAP, we see it within the file. So that's a good indication to me that yes, this is what is actually causing this bad traffic, which indicates that we found our exploit. So now our goal is to detect this, and our strategy here is going to be to identify an RTF document. We want to identify abuse of that URL moniker, and we also want to identify a potentially malicious HTTP request. So this is a Talos rule for this CVE, or one of them, because there are quite a few. And I'm going to highlight for you the chunk that actually matters, because like I said earlier, we have a header, we have a rule message, there's some other stuff down here that isn't necessarily important to the rule, but it does matter for the sake of Snort being able to organize the rules, and also just for customers reading this to be able to see that this is associated with that CVE. So if we break down the chunk of the detection that actually matters, we first see that we only want to inspect RTF files because we have our flowbits specified here. And you'll always see flowbits being used with either isSet or set, depending on if it's a rule that's going to identify a file type or some other type of traffic, or if it's a rule that's using some other flowbits rule. So in this case, we're using some other flowbits rule to identify that we are looking at an RTF. We then have our file data buffer, because we only want to look at things within the file itself. And then we look for a URL moniker. And finally, relative to that URL moniker, within the next 50 bytes of the URL moniker, we want to look for the Unicode string http://. And why, you might ask, are we including this if we just want to look for abuse of this moniker? Because unfortunately, there are people out there that are using this for non-malicious traffic. And this seems strange to me that you would need to do so, but people use things in strange ways all the time, and so we unfortunately can't block their files. And we need to add this in to make sure that we're not falsely alerting on things that are malicious. You may also know that even though I just told you it's really important, we're not specifying a fast pattern. And this is because if we don't specify, Snort will actually decide that the first longest content match in our rule will become the fast pattern. Snort defaults to fast pattern, not fast pattern only, which means that we would evaluate this as a fast pattern, and then we would re-enter the rule, and we would evaluate a second time, and be able to use a relative content match after this match for the moniker. Now I'm going to talk to you about DDE code execution, which doesn't actually have a CVE. You may have heard about this because this keeps coming up. So this is a way to execute code in Microsoft Office products without using macros. This always appears, at least in the cases I'm going to talk to you about, in a doc or a docx file. And this actually just recently came up again because we have a blog post with some research that Paul in the audience did, where this was used as a dropper, which is the way that we usually see it. So what makes this malicious? This actually gets you arbitrary code execution, which is kind of cool. And we're also doing it without macros, so there's no... this is kind of novel in that it's very different from the usual. And if we were to pop open a malicious file, we would actually see this plain text the way it is here. So this is one example of a command that was in an actual malicious sample that we saw. So in this case, it's pretty obvious to see why this is bad. We're using this to open PowerShell and execute a PowerShell command, something you should probably not ever be doing with some random file that you just downloaded from the internet. And we're using it to go grab some citibank.exe file from some kind of sketchy looking domain. So probably a good indicator that we're using this to go grab malware. If we were to pop open a PCAP of the file, we would see another command like this. We again are seeing PowerShell being used to go grab a file from some kind of sketchy looking domain. And if you look prior to DDE Auto, this little dot is indicating to us that that's a non-readable byte, which is important later on when we look at our rule. The byte is hex 13, which is a carriage return, which is why we don't see it in the PCAP. So now that we've seen this exploited in a doc file, one of our goals in our rule is going to be to identify, again, specifically doc files that are abusing this. I mentioned it briefly earlier, and all of the examples I've shown have used DDE auto, but it's also possible to use something called DDE, which the only difference there is that DDE, I believe, asks for user permission prior to executing the command. So this is a Talos rule for this exploit. And again, this is kind of long, but the chunk that actually matters to us is highlighted here in blue. And I'll go ahead and break it down in the next slide. So again, we're using flowbits to inspect just our doc files. We only want to inspect the file data buffer because we only care about the contents of the file. We then want to identify our exploit, and we want something that makes for a decent fast pattern. So we're going to use that hex 13 followed by DDE. And I'll explain why we've chosen DDE in just a minute. We then want to look for .exe appearing within 250 bytes, and the nocase makes this case insensitive. And why are we adding this content match when maybe it would be possible to use this in a way that we're not calling PowerShell? Because, unfortunately, again, this is used in non-malicious ways, not for calling PowerShell, but we did find files when we tested this rule originally that were using this in a way that we probably shouldn't be alerting on. So we have to add this second content match in order to limit our false positives. If you look at the first content match, this hex 13 DDE here, we have opted to go with DDE because if we could write two rules. We could have one looking for DDE and DDE auto, but why would I bother to have two rules if I could just have one? We want to have as few rules as possible in the rule set because it's expensive computationally to evaluate more rules. So anytime we can condense is desirable. We're also able to exploit this in a Docx file. So what I have here is a chunk of the just the malicious XML file unzipped from the zip archive. And if you read through this, you see a bunch of crap that we don't really care about. This appears in a lot of these files. And then finally we see an interesting chunk, which is this instruction text tag followed by DDE auto. And if we keep reading, this is actually a file I've neutered for my own testing, but we see again this PowerShell command being executed, and then we have a URI going to some kind of executable that's being grabbed from the internet. So this looks pretty similar to the way this is being exploited in a doc file as well. So now we want to detect just XML files from a decompressed Docx file that abuse these fields, similarly to the way they're abused in doc files. And so, again, the content of this rule that we really care about is highlighted in blue. And we're using flowbits to identify just an XML file. We then specify we want to only look in file data, and then we use our instruction text tag, which actually is required for this exploit. The reason that I know that this is required is because I spent a lot of time playing with these files, getting rid of things that probably didn't matter, and seeing if I could still get it to execute code. We then look for DDE appearing after this tag. The reason that I have distance 0 specified here is because it just indicates to Snort that at the end of this tag we want to start looking for our second content match. If you just want to look for things appearing after each other or in a specific order, you'll probably end up using distance 0 quite a bit. And then something that we haven't seen before is the use of this pseries. So this enforces that these two matches are within the same XML tag. And the way we do that is by looking for our malicious tag, and then we check that we don't see the opening of another tag prior to DDE appearing. So this is a real quick run through of the way that we use Snort to detect these malicious OLEs. These come up quite a bit because they tend to be used as droppers. It becomes increasingly expensive for adversaries to write exploits or try and gain code execution on your machine by chaining together multiple CVEs or anything like that. So this has become a trend that we're using things like phishing attacks to get a user to download a file, run it, maybe click that box that says, do you want to enable macros? In this case, you don't have to do that for either of the CVEs I've mentioned. But as we see more and more user-based attacks, this becomes more important for us to be able to detect these things. And so it's kind of cool, at least in my opinion, that we're able to use a network IDS in order to detect things like bad RTFs and doc files. I hope that you've maybe come with some kind of understanding of Snort that has been improved a bit on how you can differentiate just writing a Snort rule versus writing a good Snort rule that's actually useful. And something cool that I didn't mention earlier, maybe I did briefly, is that this is actually free and open source. So even if you don't spend millions of dollars on our security products, you can actually go grab Snort for your own personal use. And we have a free community rule set. A lot of people submit rules to us. Someone on our detection response team will evaluate them and clean them up a bit, and then they'll be added to our rule set, which is then also actually released to our customers. So you too, if you are submitting to our community rule set, are helping to improve the internet a bit. So if you have any questions for me, I'll go ahead and take them now. Otherwise, thank you, and you can go ahead and, if you feel so inclined, and follow me on Twitter, or the Talos Twitter account as well.